Hello, in this video we'll continue our discussion of mixtures by exploring phase diagrams for these systems. We'll start by looking at two-component phase diagrams corresponding to Raoult's law and then move on to those corresponding to deviations from Raoult's law, which leads to azeotropic compositions. So just as a refresher, here's a diagram that shows the pressure versus mole fraction composition corresponding to Raoult's law, where Raoult's law is given by this simple relationship between the pressure of a substance in a mixture being equal to the pressure of the pure substance times the mole fraction in the mixture. And of course that means that we've got a linear relationship as indicated here for substance P sub A. And then for substance P sub B, we also have a linear relationship. And of course, the total pressure is also a linear relationship. Now, again, just as a reminder, while these expressions may look like the Dalton's law expressions, the mole fractions in the Raoult's law equations correspond to the mole fractions of the substance in solution, not in the gas phase. Dalton's law relates the partial pressure of a gas to the mole fraction in the vapor phase, and that it is multiplied by the total pressure to get the partial pressure. So you'll notice that we're using a different symbol or term for mole fraction in the vapor phase here so that we don't get them mixed up. So from this point forward, we'll use X when referring to the mole fraction in solution, and we'll use Y when referring to a mole fraction in the vapor. Now, the diagram on the previous slide corresponded to pressure of the vapor as a function of mole fraction. This diagram shows an actual pressure composition phase diagram that includes both the liquid and the vapor phases in our diagram. So, for example, down here at the bottom you'll notice that we have Z representing mole fraction as opposed to X or Y, and we'll use Z to represent the overall mole fraction, and that means combining the vapor and the liquid phases together. In this diagram at high pressures, we'll notice that we have liquids, so any composition and pressure falling in this orange region here, if we have something in that region, that means we have entirely liquid. In the lower region, we'll have entirely vapor, and in the region between these two, we have a liquid-vapor equilibrium going on. So let's start with a situation where we have a pressure and composition corresponding to the point labeled D here in this diagram, and let's increase the pressure. We just follow the arrow upward until we reach the boundary of the liquid-vapor equilibrium. At that point, we find the vapor begins to condense into liquid, and that the composition, and if we raise the pressure even further to point C, we have a situation where we are in equilibrium, where the pressure over here on the boundary corresponding to the liquid corresponds to the mole fraction of substance A in the liquid phase. And over here on the right, where the point intersects the boundary for the vapor, that corresponds to the mole fraction of A in the vapor phase. So we'll note that we have this horizontal line here that connects the two regions, the liquid and the vapor region, and the endpoints of that line where it intersects the boundaries corresponds to the mole fractions of the liquid and the vapor respectively. Okay, so now we're going to take a look at the phase diagram curve where rather than plotting pressure along the vertical axis, we're plotting the temperature of the boiling point. All right, so we could, for example, in this case, we're looking at a mixture of benzene and toluene at 1 bar pressure. Over here, where the mole fraction of benzene is equal to 1, the temperature at the curve at that point is a boiling point of benzene, and on the left side, where the mole fraction of toluene is equal to 1, we note that the point on the curve corresponds to the boiling point of toluene. And then we also know, of course, that at low temperatures, the liquid phase is going to be the more stable. As we raise the temperature, the vapor phase is going to be the most stable. And of course, in this region in the middle, this bounded region corresponds to the liquid-vapor equilibrium, just as it did in the previous slide where we had pressure plotted along the vertical axis. Okay, so let's see what happens here if we start with a benzene toluene mixture at a temperature indicated by this little dot, and we raise the temperature. Well, we raise the temperature until we get to the point of intersection of this envelope curve, and at that point we're going to see the first bit of vaporization occurring. So the first bit of vapor comes off, and we will note then, as we did on the previous slide, that the mole fraction of the vapor that comes off is indicated by point B here on our diagram. So we'll note that the mole fraction of benzene in vapor at this point is greater than it is in the solution. We started out with a solution mole fraction which was maybe just a little bit greater than 0.1, and in this case we have a vapor mole fraction that is on the order of, say, 0.21 or 22. So in any event, the point is that we have enriched the vapor relative to the solution, that the vapor is now richer in the more volatile component, which is benzene, because it has a lower vapor pressure, a lower boiling point, higher vapor pressure, so that we can see that this is one way to actually generate a mixture which is purer in the more volatile substance. So we can go through a set of cycles here where we can just continue to go through this situation of vaporization and condensation. We'll also note over here, actually, forgot to mention this issue, that while the vapor is going to be richer in benzene than is the solution, it's going to have a lower mole fraction in the toluene than is the case in the solution. And again, the vapor becomes richer in the more volatile component. All right, so what happens then if we take the point B, all right, and the vapor at point B, and we lower the temperature so that we get condensation into the liquid phase? So we're condensing it. Now we have a solution which has a mole fraction in excess of 0.2, and then we heat that solution. And when we heat that solution again, when we reach this particular point, we're going to get vaporization, and the vapor that comes off is going to be even richer in benzene. In this case, it looks like it's close to 0.4 on the mole fraction. So then we take that and condense it and vaporize it, and we can see that we're going to just continue to follow the cycle indicated by the blue lines here until we get to the point where we have pure benzene. So we've gone through this process of vaporization, condensation, going through several cycles until we end up with pure benzene. And of course, this is known as fractional distillation. This is exactly what happens. You boil it, you condense it, you boil it, you condense it, you boil it, condense it, until what you end up with coming off the distillation column is the pure substance, and the substance that we're going to get that's purified is the one that has the lower boiling point, that's more volatile. All right, so now what happens if we have deviations from ideal behavior? The previous curve corresponded to a situation where the benzene toluene mixture was an example of an ideal solution that followed Raoult's law. We also know from previous conversations that we have deviations from Raoult's law. And here's an example of a phase diagram for one of those deviations in which we have what's called a high boiling azeotrope. This is going to correspond to a situation where we have negative deviations from Raoult's law, which means that the pressure is lower than predicted from Raoult's law, and also means that if the pressure is lower, the boiling point is going to be higher than is predicted from Raoult's law. You may recall that negative deviations correspond to situations where the interactions between the solute and solvent, or between the two components of the mixture, are actually stronger than the interactions of the isolated components. So these very strong interactions create the negative deviations from ideal behavior. All right, so if we look at this, we see a definite maximum in our phase diagram, and the composition corresponding to that maximum is called the azeotrope. It's the azeotropic composition. And what we'll note then is that if we have a composition exactly at the azeotropic composition, then we cannot distill it. If we start out with that composition, we're going to heat it until it reaches the boiling point of the azeotrope. So there's our boiling point of the azeotrope. If we continue to heat it, it's just going to boil into vapor. So at no point do we actually change the composition. The composition of the vapor that boils off when we boil the azeotrope is the same as the composition of the initial azeotrope. However, if we start at a composition that is different from the azeotropic composition, we will get some distillation. We'll see here if we start out on the right side and we heat it, we're going to get condensation, and we're going to get this process where, just as we noted on the previous slide, we go through the cycles. We go through the cycles, we end up with pure substance A. What's different about the azeotropic system is that if we start out to the right of the azeotropic composition, at higher compositions we get pure A. If we start out on the left, we're going to get just the opposite. If we go through the cycle again of evaporation, condensation, evaporation, condensation, we're going to end up with pure B. All right. So depending on which side of the azeotropic composition we start, the end product of distillation will be different. Obviously, if we have a high boiling azeotrope, we have to have a low boiling azeotrope. This is a graph that shows that phase diagram for a low boiling system. This is going to correspond to a situation where we have positive deviations from Raoult's law behavior, where the pressure is greater than that predicted by Raoult's law. And remember again, this corresponds to weaker interactions, where the AB interactions are weaker than the interactions of the individual solute and solvent or pure liquids at this point. So since we've got greater vapor pressure, then we're going to note that the boiling point is lower for this azeotrope than is the case that either of the pure substances. So again, let's look at what happens when we do a attempted distillation. In this case, we start over here on the left and we heat it. We're going to reach boiling, and of course when we reach boiling, we're going to end up with a situation where we create vapor at that composition. But if we go through the process again of the cycles of vaporization and boiling, what we're going to end up with is we're not going to end up with a pure substance, we're going to end up with a substance at the azeotropic composition. So we're not going to end up with pure A or pure B, we're going to end up with a substance at this particular azeotropic composition. And it doesn't matter which side of the phase diagram we start. If we start on the right, we're going to end up with that. If we start on the left, we're going to end up with the azeotrope. So in both cases, we end up with the azeotropic composition. We cannot get a pure substance through the distillation process. Benzene and water, ethanol and water are an excellent example of this type of mixture. If you take an ethanol water mixture and you distill it, you will reach the azeotropic composition, which is roughly 95% ethanol, and that's as close as you can get through this simple two-component distillation process. So here's a table that shows various examples of various azeotropes and the boiling points. For example, the water ethanol mixture seen here, 100 degrees, of course, is the boiling point of water. The ethanol boiling point is 78.5. We'll note that the azeotrope has a boiling point of 78.2. Notice, of course, that the boiling point of the azeotrope must be lower than the boiling point of either of the substances in their pure state. That makes it a low boiling azeotrope. In this case, it's 78.2, which is only slightly lower than the boiling point of pure ethanol, which means, of course, that the azeotrope is close to 100% ethanol, but not quite. In terms of mole fractions, you can see that the mole fraction of water here is roughly 10%, 9.6% in this at the azeotropic composition. All of the substances in this particular table are low boiling azeotropes. You can see in all cases the boiling points listed are lower than the boiling points of either of the pure substances. So these are all low boiling azeotropes here listed in this particular table. So this ends our discussion of mixtures and phase diagrams for mixtures. In our next video, we will begin our discussion of colligative properties. So stay tuned.